Swayam Prabha. Digital India. Educated India.
So let's start with where we left off. This is just a formula for force on a particle. So you have a particle, and if we want to calculate what the force exerted on the particle by the surrounding fluid, you take the total stress dotted with n, normal surface normal vector, that is this is called the tractional force on the surface, and then you integrate over the surface. So that's the standard. The only thing that I've done here is this total stress in the fluid. We say, okay, there is an undisturbed flow. This is the undisturbed stress, and this is the stress due to the perturbation. And this first term is what gives you this. So in other words, the undisturbed flow integrated over the volume of the particle will yield a force. So this is what I earlier talked about, is this gives rise to buoyancy force and things like that. Okay. Now when you put the particle, it perturbs the flow, it makes the flow go around it, it will make the flow satisfy no slip, no penetration, and so on. And that creates a perturbation flow whose stress field is sigma. And when you integrate that on the surface of the particle, you get three terms. The first of this is what we have seen in the previous lecture, the Stokes drag. The other two terms are, now the flow is unsteady. So these two terms, you will call them unsteady effects. If the flow is slowly varying, you don't need these terms because everything is happening so slow. But if the flow is an oscillatory flow, if you have a particle and let's say it's subjected to waves, well then you will have to worry about these additional terms. So depending on the problem, or you have a propeller or something, your flow is periodically changing, and you have a particle or something is there, and everything is changing in time, then you have to worry about it. Or a pipe flow where your flow is oscillating. Okay, then you have to say, okay, my flow is unsteady even without the particle. Therefore, what do I do? There may be additional forces. Okay, they are called added mass and Bassett history forces.
Yeah. So the origin of the undisturbed flow force is not unsteadiness, right?
It's not unsteadiness.
So it will be present.
No, actually, it's a great case. This gradient of P is what probably, see, many of them think of it this way. You have a pipe flow, okay, and let's say you have a tiny little particle in there, and the pressure gradient is such that the flow is going back and forth. Now, how do you make that flow happen? You will have to apply a pressure gradient. You send the flow this way, then the pressure gradient will go back this way. That pressure gradient will create a force. The pressure gradient was necessary to make the flow unsteady. Okay? But what I am trying to say, the undisturbed flow, just the fact that it is time varying, there will be a force on this thing. It's sort of like a buoyancy force. Okay? Now, when you put the particle, you will have wake behind the particle, the Stokes stress sled, all sorts of stuff that I talked about. Now they are all unsteady. They are varying in time because the flow around you is not steady anymore. So you have additional effects due to the perturbation flow. Okay, so that's this. Okay, makes sense?
For example, Poisson flow is created by a pressure gradient. So there, this undisturbed flow force always there because it's already steady.
Yeah.
So what I want to say is that in the Paxson correction also this force exists. It's not coming only here because of Paxson.
Yeah.
Correct.
You're right. This term can be there always. You're absolutely right. Yeah. So that's why I don't want to call that unsteady flow force. It is. You tell me what the undisturbed flow force is. This is actually very, very simple. It's nothing but, this term is very simple. Let's say you have a particle here. Your undisturbed flow has a stress field, dot with n and do the surface average. This is the undisturbed flow force. This is just writing it out. Okay, this is just, it comes out to be this. Okay, so basically you take the undisturbed flow, integrate it on the you take what happens on the surface of the not the actual particle where the particle would have sat. Okay, you do a surface integral, and that's okay. So what I'm going to do now is look at all these four forces in a little bit more detail, and this is exactly goes back to his question. See, undisturbed flow force is nothing but this term. So you take the undisturbed flow and you ask a simple question, hey, I have an undisturbed flow, it could have a pressure gradient, whatever it is, even in the Paxson's correction like you pointed out. It doesn't have to be unsteady, it could be a steady flow. You just simply ask, what is the force on this volume occupied by the particle? That's the force that will anyway be there, and typically you can write it as a pressure gradient force and a viscous force, etc. Okay, so for the BBO case, if the undisturbed flow is uniform, if a flow is uniform, it doesn't have any gradient, so there is no viscous stress. It's only pressure. Okay, so in the BBO equation, that's why what you get is the pressure gradient force due to the undisturbed flow. Okay. For example, this pressure gradient could be simply due to buoyancy. In other words, if you have as you go down, pressure is increasing, therefore you get a buoyancy force up. Okay. So undisturbed flow is not a problem. Okay, so it's always easy to compute. Okay, so there is nothing difficult about this. The quasi-steady force is also not a big deal, because we are saying, okay, the flow is changing in time, but can I take the flow at any instance and think of it being steady? The flow is, say, in an oscillatory flow, at any instant you capture what the flow is at that time, and then you calculate Stokes drag based on that instant, what the velocity at that instant. Okay. Now I should point out that sometimes I write this V, sometimes I don't write this V. Keep in mind that you can have a particle stationary and the fluid oscillatory, or you can have the fluid stationary and the particle oscillating. Both are the same. This is called Galilean invariance. How many of you heard of Galilean invariance? Okay. Galilean invariance means, that's very, very important. That's true for any model. Okay. All your models have to be Galilean invariant. So in other words, the previous equation, this equation, if you write an equation like this, so this is the model for force, right? This model must be Galilean invariant. Galilean invariant is nothing but if you chose a coordinate system that's moving. So in other words, if the observer is moving, it shouldn't change the answer. Okay. And that is why everything appears as difference in velocity. Galilean invariance says that, say, if you have a pipe flow, so this particle is stationary, and let's say the fluid is flowing, okay, parabolic velocity flowing. Now this is in a lab frame, so the particle is stationary and the flow is coming left to right. Suppose you take this and you mount it on a car or a truck and you are moving at constant velocity. Galilean invariance, not an accelerating frame. It must be what is called an inertial frame. So, if you are moving at constant velocity and I am moving here, I am not supposed to be moving, but if I move, you will see that the particle is not stationary from my perspective. From a lab frame, it is stationary, but if an observer is moving, the particle is moving, but the fluid velocity also correspondingly changes. The difference in velocity is not changing, it is observer independent. Okay, so that's the important thing. So, just by looking at this and I say, okay, this is good. If, for example, if I didn't have this term, it wouldn't be Galilean invariant. Okay, so some of those features are very important. So, you can see this is the Galilean invariant form, and therefore, quasi-steady drag depends on relative velocity. In other words, what is the velocity of the fluid seen by the particle? If the particle is also moving, it will see only the relative velocity. So this I don't want to elaborate anymore because we spent a lot of time. Now, I wanted to think in terms of what is added mass force. The added mass force has this form. Okay. Now, again, it's in Galilean invariant form. So, in other words, you care about how the fluid is accelerating compared to the particle. So, we could think in terms of fluid stationary and particle sort of accelerating, or you can think of particle being stationary and the fluid accelerating, and it does not matter because only the difference matters. Okay. So, in other words, one way to think of it is move with the fluid and you look at the fluid, move with the particle and look at what the relative acceleration seen by the particle. Okay. Now, what is the meaning of this added mass force? When you think of a swimming pool and you have a ball, a particle, and you drag in the swimming pool versus the force you have to exert when the particle is in a vacuum. If it is in a vacuum, if you want to accelerate the particle, how much force you should apply? Very simple, mass times acceleration, Newton's law. Now, when you want to accelerate the particle in a fluid, easy to think in terms of water because then you can realize it, you not only are accelerating the particle, you are going to accelerate a certain halo of fluid surrounding it. So, the force you must apply now is not just mass of the particle times the acceleration. You must apply an extra force to accelerate a halo of fluid that goes with it. So, in other words, you have to apply extra force, and that is why it is called the added mass force. Now, you want to accelerate the particle surrounded by a fluid, and the fluid is also accelerating, then there is no problem. It is anyway accelerating. That is why what matters is the relative acceleration. You want to accelerate a particle in a medium different from that of the surrounding. You have to apply a force not only to accelerate the particle, which we all know, but you have to do an extra force. And where does the extra force come? It is only due to no penetration boundary condition. It could be an inviscid fluid, does not matter. Just the fact that the fluid cannot penetrate through this particle and you accelerate it, it will drag with it a certain amount of fluid. An added mass must be accelerated, and that is the idea of added mass force. So, if you have a particle of certain volume, if it is spherical in shape, you are accelerating half the volume of surrounding fluid. And that is where this 1/2 mf comes. Mf is nothing but mass of the displaced fluid. So, in other words, the lesson is you want to accelerate a particle, you are going to accelerate a certain added mass of fluid with it. For a sphere that extra fluid that you are accelerating is half the volume of that particle. Now, on the other hand, if you have a ellipsoid and you are accelerating, the ellipsoid is in this manner, you can already see, wow, added mass is going to be not half, it's going to be maybe 3/4 or 4/5. So, in other words, added mass is particle shape dependent. On the other hand, if you have a particle like this and you want to accelerate, you can easily imagine that the amount of fluid that's being pushed around due to no penetration boundary condition may be lower. So, the added mass of this may be only 1/3 or 1/4. So, added mass is a very geometry dependent quantity, and it's nothing to do with viscosity. It's only due to no penetration boundary condition. It's an inviscid force. Okay. So, is that clear? So, this is what I said. If you want to accelerate a particle, in vacuum you would need mass of the particle times acceleration. You want to accelerate the particle in a stagnant fluid, you got to apply this extra force in order to accelerate the added mass. You're going to accelerate a certain amount of fluid. Yes.
So, sorry. Added mass due to no penetration.
Yeah.
Can the no slip boundary condition?
Next slide. Next slide is that is the effect of viscosity. Okay. So, you are absolutely right. So, if you take this particle, take the case of a plate, added mass, and you are accelerating this way, added mass is 0, because no penetration boundary condition, nothing, it's just a plate, so it just goes. But viscous effect will be there, the boundary layer will be. So, for the plate, added mass coefficient is 0 in this orientation. In this orientation could be 1. Okay. So, that is where the physics of the problem comes. Yes.
So, sir, as far as I have understood, so we are trying to account for the displacement of the particles, fluid particles. Like our solid is moving and it is displacing the fluid in this direction in the equivalence of the equivalent mass of the fluid.
Yeah, yeah. So, in other words, think of it this way: a sphere there is a certain amount of fluid stuck to it, think of it this way, and that volume of the fluid is half the volume of the particle for a sphere. For this plate, the amount of fluid that stuck to it is 0, because no penetration wouldn't, but like the point he was trying to make, the viscosity will create some added, you cannot call it added mass for the viscosity, we will get to it in the next slide. But think of it like an inviscid fluid. Okay, now, okay, no fluid is being dragged by viscosity, fluid is being pushed around only because of particle saying please move, I got to come. So, it pushes the particle away. So, the inviscid mechanism.
So, the surrounding particles are being pushed away to make the path.
That is right, surrounding fluid. Surrounding fluid is being pushed away by the thing. So, this is just basically potential flow. This answer comes simply, you can do a potential flow and get this answer. Okay.
For example, I have a small gas bubble, and if I say extremely small tiny gas bubble, for example, less than 5 mm size, 3 mm size, the cadre must be has to be taken up.
Now, if it is steadily rising, this is all for acceleration. If a particle is moving at constant velocity, no problem. You must have relative acceleration. Look at this. You can have both the fluid and particle accelerating the same way, it does not matter. For example, take a Coke can in your, or put a particle in a fish tank, and if you are accelerating in a car, everybody is accelerating. So, no, it is a relative acceleration. You must have one accelerate with respect, the particle must accelerate with respect to the fluid. A rising bubble is constantly rising, or a falling particle is falling down at constant velocity. Sure, it is asking it to push, but there is no acceleration, so there is no force associated with that by Newton's law, right. If constant velocity, no force, So no force for the particle, no force for the fluid, except the viscous part will come as drag. We are only talking about the inviscid part.
But the size of the bubbles will change as per the gravity and the height.
What is that?
Size of the bubble will change with respect to the gravity.
No, that's what I'm saying. Size of the bubble, the velocity will change, but my question is there acceleration, relative acceleration between the particle and the surrounding fluid? If it's rising at constant velocity, there is no acceleration. So if you held a bubble and suddenly release it, there will be added mass force till it reaches the final velocity. Or you drop a ball in the water and it's falling down. Initially the velocity is 0 and it has to accelerate. When it's accelerating, it must accelerate a certain amount of fluid with it. And again, this force is fairly well understood because it depends only on potential flow. The important thing is that this coefficient half is only true for a particle, okay, or a spherical shape. Now, same thing happens. It's a little more complicated, but this is due to the fact that when you accelerate a particle relative to the fluid, so again you have the same thing, relative acceleration. Now again you have to apply additional force because fluid is being dragged with the accelerating particle. But now how much you are dragging is not a constant anymore, because of the viscous boundary layer, how it grows over time. I don't know whether you have studied, the boundary layer grows as square root of nu t. The thickness of the viscous Stokes layer changes. So that's why what happens is that here this is a much more complicated problem. In other words, your force will depend on what you did previously. So this is why it's called the history term. If you accelerate a particle, the added mass immediately will act instantly. If you accelerate, he says push away, make way for me because of the no penetration boundary condition. On the other hand, the viscous boundary layer will slowly develop, and as it develops, it will say more and more force will be required. Okay, so this is an exact derivation, and always the viscous effect of acceleration will appear as an integral. That's because boundary layer grows. The one other way to think of this is in the potential flow, there it is acoustic signals going. So when a body moves, the inviscid effect is to say push. Okay, so a acoustic wave. But in an incompressible flow, that acoustic speed is infinity. So instantly the whole flow knows I got to move away. Whereas the viscous effect, the viscous wave will take time to propagate. It moves at finite velocity, and therefore it appears as the integral term. So the point finally is that when you have a particle subjected to uniform flow, no spatial variation, only thing is that you could move the particle in a time dependent manner, or you could keep the particle and move the flow in a time dependent manner, doesn't matter. This formula applies. There are 4 forces. One is the undisturbed flow force, quasi-steady force, added mass force, Bassett history force, and you have to add all 4 of them, and that will give you the total force. Any questions on that?
Sir, I have a question. So, sir, this Bassett history force, the particle does not know what is the force it is experiencing. For the particle, it is always the undisturbed flow, correct? Undisturbed force. So, the thing is, the particle we have a particle in a fluid. Whatever fluid it is coming towards the particle, so it is like an undisturbed flow for the particle. But I could not understand the Bassett history, the origin of Bassett history force.
No, the undisturbed flow, the particle knows the perturbation. Particle is making the flow change around it, right? So if you have a stationary particle, flow is coming, so you go to a bridge and river is flowing. The bridge, the pillar will say you can't move. The fluid has to go around. So what's the force on that pillar, or in this case a particle, is the effect of the fact that it has perturbed the flow. Okay, so it makes the flow go around it. Okay, now what happens is that suppose you have a particle subject and you have a flow. You have a certain flow going. Let's say you have a boundary layer. Now suddenly you double the flow. The boundary layer has to become thicker. It doesn't happen instantly. It just takes a time to grow. During the time, the force on the particle keeps changing slowly, and that's this term. So imagine that you suddenly change the flow from 1 meter per second to 2 meters per second. You accelerated the flow, very short time. There is a inviscid effect, which is the added mass force, that immediately will show up a big spike in force because you accelerated and it will. The viscous effect will happen on a slow time scale, and this is called the viscous history kernel. In other words, this tells you how the fact that you accelerated, so this decays over time. As time increases, it goes as 1 over square root of time. Right? So the fact that you accelerated immediately creates a force, but then it lingers for a long time and it dies. That's the physics of this problem. Why it's happening? Because when you change the velocity from 1 meter to 2 meters, the boundary layers change, the skin friction on the surface of the body change, and it takes a while for that to complete its job. Okay? And that's the meaning of the Bassett history force. That's why when a flow is unsteady, you have all these complications coming. In a steady flow, the Stokes drag, the quasi-steady drag, was easy because that is the effect of the fully formed boundary layer. Viscous effect, pressure effect, everything is steady, so you have nothing to worry. Now when you change, it has to go from the old value to the new value, and it doesn't do it instantly. It has to build up. And that's the history term. Yes.
How does the density ratio affect the Bassett history force?
Density effect?
Density ratio of particle and
Well, no, actually, density doesn't play a direct role. Okay, it's a great question. See, when you look at this problem, density will play a role, but in a backhanded way. When you have water, and let's say you drop a sand particle versus a ball of steel or something, things change. Okay, that change is not because the formula has changed. It's just that the velocity will be larger for a steel ball. So in other words, the formula is applied whether it's density ratio is 1, 5, 10, etc. Okay, but when you apply this formula for different cases, the answers will be different because you're balancing forces. Okay, did that answer your question? So density ratio, the quick answer to your question, no, density doesn't play a role in this drag law. Okay, so maybe your answer to your question may come better in this one. So let's do a simple example of a particle being dropped. Okay, so you hold the particle and you let go. So this initial velocity is 0, the particle's velocity is 0. The good news is that in this case the fluid is stationary. There is no fluid moving, undisturbed flow is 0. So this will be your equation of motion, which is mass times acceleration of the particle is sum of all forces, Newton's law. This is external force on the particle, and F takes care of all the fluid forces, whatever the fluid applies. And there are 4 terms that we talked about. This F, undisturbed flow, quasi-steady, added mass, and Bassett history. Those are the 4 forces. Now, you can write all of them because I gave you the formula. So, undisturbed flow, I said it many times, will come out to be buoyancy force, just upward. Okay. Is mass of the displaced fluid times g in the opposite direction. Okay. So, that is pretty easy. Quasi-steady force is fluid is not moving, only particle is moving at velocity v. So, you get this formula. Added mass force, similarly, fluid not accelerating, the undisturbed flow is just a stationary fluid. So, this formula is there. And Bassett history is the only complicated thing, then you can put in there. And you do some simplification and you get this equation. Okay. So, you can solve this to calculate, this is just a simple ODE for the vertical velocity of the particle, and it will go from 0 and it will accelerate and it will reach its final settling velocity. Okay. So, this is so particle velocity, finally particle will stop accelerating, this will become 0, this will become 0. So, your v will be equal to settling velocity. Okay. And how fast it will approach, that is why you see this term tau p come here, is the time it takes for it to go from 0 velocity to its final velocity. Okay. If it is a big particle, it may take a long time for it to reach its terminal velocity. A small particle will quickly reach its terminal velocity. But this is including all the effects, and of course, this whole thing is true when Reynolds number limit goes to 0, because everything that we studied so far is Stokes limit. So, for very small particles, this is applicable. So, this is one application of how you use those 4 forces. Okay. You can take the case and you can apply.
C here is the sign, is it? D.
T?
C, yeah, that symbol C.
Z?
The
Yeah.
Bassett
Okay. No. Yeah, let me go back and. Okay. See. Okay. Good question.
So the limit here is from minus infinity. That's right.
Yeah. Yeah. I will explain. Yeah. It's a good question. So, let us look a little bit. I rushed through. So, what we are trying to calculate is what is the Bassett history force, which is due to boundary layer growth, I said, at some time t. So, you are asking, a particle is asking a question, hey, Bassett history, what is my force right now? Okay. The answer is, if you want the force at time t, go back in time from the beginning of the universe. Okay. Okay. In other words, everything that happened before, you take care of all the relative accelerations of the past. They have been evaluated at some time kz. Kz is the cumulative action of all the past. This is called a convolution integral. I want to know what happens now. I have to take care of everything that happened in the past. In this case, everything that happened in the past is all the relative accelerations of the past matter, but not equal weight. So, this is the weight. This is usually represented as kernel. Okay. It's written as t minus. This kernel is decaying. In other words, everything that happened in the past is continually getting less and less important. Okay. Here the decay is 1 over square root of time. So things that happened 10 times earlier will be 1 over square root of 10 times less important. Things that happened 100 times earlier is 10 times less. So that's what happens. So is that everything that happened in the past gets integrated to find the time now. So in other words, a Bassett history, all the boundary layer growths, changes that happen from the past, all the accelerations, it's like karma. Okay, basically that's what it is. All your previous actions will have an effect now, and it's also causal. What you're going to do next has no effect on you. So your force at time t depends on all your past accelerations. Okay, very different from here. Added mass, which is the inviscid effect, is instantaneous karma. You do something, you have relative acceleration, you get penalized right now. Right there you have an extra force. Here all your past actions will cumulatively act. Okay. Did that make sense?
Why did we choose to write, just a matter of convention, why did we choose to write 0 to t?
What is 0 time? I mean,
Where it starts, then maybe.
okay, if you say, if you start at 0, everything. So if you say there was no acceleration before 0, then automatically this becomes 0 to t. If you say that you are going to start, I mean that's just a technical detail. Okay, minus infinity basically simply says everything that happened in the past matters. That's all it's saying. Whether you call it t equal to 0 or something doesn't matter. Okay, so all I'm saying is all past actions will have an effect at time t. And this is a very important question. This decay is very slow. 1 over square root of time is really slow. Okay, you will turn out later that this is not reality. It decays exponentially. That means typically in any application you don't have to go hours or days back. This kernel, this guy, decays quite fast. So what happened maybe the past second or 2 seconds, maybe 10 seconds, depending on the problem, that's all matters. Okay, because memory is lost. Okay, typically. Okay, but this is the derivation for 0 Reynolds number. So 0 Reynolds number, things don't forget very fast. At finite Reynolds number, things are forgotten fast, and that will show up in this k. The k will change with Reynolds number. Okay, but this is the theory behind why Bassett history term appears, and this integral makes it very hard to compute, and therefore most people just hand wave and ignore it. Okay, that's what people do. But here you have, if you, in some problems it could be important and you have to take care of it. Yes.
How do you arrive at the weightage of that kernel?
Bassett, Boussinex, and Oseen derived it. Okay, derivation is in the paper. It's a little more complicated. Okay, but this is analytically. They solved Stokes flow for a moving particle. So in other words, see what these guys have done is they solved the difficult Stokes flow, unsteady Stokes flow equation. They solved around a sphere, and then gave us this final answer. Now keep in mind the final answer doesn't look simple, but it's much simpler than solving the whole equations. Okay, so that's the difficulty, that these models have greatly simplified the fluid mechanics problem, but yet they end up still being somewhat more complicated. Imagine you solving the boundary layer thickness every time, so let's say using a CFD, that's a lot of work. It's much nicer to have just a formula. You just have to do this integral and you have the force, and it is exact in the 0 Reynolds number limit. So that's because they have encoded all the fluid mechanics at the small scale, taking into account the perturbation, and the answer comes out to be this complicated term. Now, so Bassett-Boussinex equation was in the 1883 or something like that. Okay, and then people tried to put Faxon and Bassett together. So in other words, complicated spatially varying flow, temporally varying flow, and it took 100 years to solve that problem. Okay, there was no good solution. Finally, Maxey, Riley. It's just amazing. These two guys, Maxey and Riley, solved it in 1983. Exactly same year in France, Gatignol. They both waited 100 years, and then they solved on the same year, both of them. Of course, there are other people who have gotten. They almost got these kind of relations, but they never made it perfect. Okay, so what I wanted to say is that's called the Maxey-Riley-Gatignol equation. Now you may look at it; it's exactly the same as what I had for BBO equation. So what's the difference? Okay, so I haven't made any change, and I will tell you what happens. So you remember Faxon just said, oh, just take the surface average velocity. So the Faxon would say, okay, don't take this uniform velocity, but just take the undisturbed flow on the surface of the particle. Okay, it turns out that you just have to do the same thing. This is average over the volume of the particle. You take this surface of the particle, you average this over the volume of the particle. That's it. So it took a long time. What they found was, yeah, BBO equation is good, but only thing is that the undisturbed flow, you either have to average over the surface of the particle or over the volume of the particle, depending on which force that you are looking at. If you want added mass force and undisturbed flow force, do a volume average over the volume of the particle, okay, undisturbed flow quantities. But if you want viscous terms, which are the quasi-steady force and Bassett history force, you have to calculate them, average over the surface of the particle, and just use it as if it is a the Bassett-Boussinesq equation. So, and again, the derivation is a little complicated. You can read both these papers. They don't have exactly in this form, but this is the current understanding. This is the how you will model them. Okay, so what we have done so far is just one particle, so a lot of work, just one particle and 0 Reynolds number. Okay, what we have gotten now is, yeah, any kind of flow we know how to calculate the force at the end of the thing. Okay, now where I want to go next is what happens when the Reynolds number is finite. Okay, and I want to spend a couple of minutes on that. I just want to take, so we have 4 terms, right? Undisturbed flow force, quasi-steady force, added mass force, Bassett history force. And we know volume average, surface average, etc. will take care of spatially varying flow. Now the question I am asking is, what happens if Reynolds number changes? Very simple question. Undisturbed flow force doesn't change at all, okay, because that's by fundamental definition is the undisturbed flow. You have a particle, you do surface volume average, and that's the force. So there is nothing to talk about. Now the quasi-steady force is where many of us that's the most important force, and let's talk about how it changes with Reynolds number. So Stokes drag, and this is the term that we have been using, 6 pi times viscosity times radius of the particle and the relative velocity. Quasi-steady force depends on relative velocity. Now this formula is good when Reynolds number is 0. At small Reynolds numbers, Osin did some expansion and he gave this analytically derived this formula, but nowadays nobody really uses this thing. Okay, the popular one is at finite Reynolds number, you multiply the Stokes drag with what is called finite Reynolds number correction. There is no analytical theory for it, you just experimentally verified. You can do CFD, microscale simulations, particle result simulation at finite Reynolds numbers. You can use open form, fluent, whatever you want, and you get the Reynolds number as a function of time divided by Stokes drag, and whatever left behind is the correction. And this is one good formula. I use it all the time. It's very efficient. Okay. But this formula is good for Reynolds number up to 20,000, 30,000 like that, and afterwards you all know that it reaches a constant value after a while. Okay. So in other words, the point is that why did we spend a lot of time in deriving BBO and Maxey-Riley-Gatignolle equation is because everything else is built on top of that plan. That is the basic form, and we are just going to tinker with that. So if we don't understand what we started with, it's not going to be very easy. So finite Reynolds number effects are always going to be written as some correction. Okay. So for the quasi-steady drag, it's the finite Reynolds number correction. Now later we will see this is for one particle, right? You may ask, what happens if there are many particles? Same idea. We will add another correction for finite volume fraction. There is not one formula, but there are a variety of formula, and you got to pick. Now where it's coming from is basically from this kind of an idea. Okay. So this is for quasi-steady force. Now added mass force, the good news is that it doesn't change. Okay, it doesn't change. Only thing is that the technical detail is that this d by dt, it changes to that d by dt term changes to total derivative. Okay, just a technical detail that what happens is that when nonlinearity comes in, the fluid may not only accelerate in time, but there can also be what is called convective acceleration. Okay, because you see in Navier-Stokes you don't just use time derivative, you use total derivative, right? So then you say, yeah, when I have to calculate relative acceleration at finite Reynolds numbers, you have to take total acceleration of the fluid minus acceleration of the particle. For acceleration of the particle, it's a rigid body, therefore there is no convective part, you just have time derivative. Okay, so that's a little change, but otherwise added mass coefficient doesn't change with Reynolds number, fortunately. So the bottom line is that pressure, the undisturbed flow force and the added mass force remains the same. It is the viscous effect really becomes hard. Okay, for the quasi-steady force, you have a finite Reynolds number correction. Bassett history force, previously whatever we had, and somebody asked the question, where do you get that? That was derived analytically for 0 Reynolds number. At finite Reynolds number, you just have to do some CFD or experiments to get this coefficient, this kernel. Okay, so previously it used to be this, but now it changes. I mean, you look at equation 4.134 in the book. So those are empirical. So everything finite Reynolds number means we will do empirical corrections. Okay, that kernel at finite Reynolds number, you gotta cannot be derived from theory. It has to be fitted from some simulations or experiments. Okay, and this is why a lot of people do particle resolved simulations. Is mainly to get these kind of corrections. Okay, and these corrections get multiply some theory that people have derived at low Reynolds number. Okay. So this is how it looks like. This line, this green line, this is basically in log plot. K is nothing but, remember, how much you're going to weight the past. Right, 10 to the power minus 3 seconds, you weighted by whatever this value is. And you can see 10 power minus 2, 10 power minus 1, a second earlier, 10 seconds earlier, 100 seconds earlier. What happened? Those relative acceleration. This tells how much you should weigh that. Okay, that's what the kernel is doing. So somebody asked the question, minus infinity to infinity. If I want the force now, I got to integrate everything that happened from a milliseconds to a second to 10 seconds to 100 seconds earlier. you look at this and you may say, well, I don't have to care anything that's less than 10 to the power minus 2. Then you say, okay, 10 seconds is what the memory, afterwards it dies. So this tells you how much back you need to really calculate. Now the green line is terrible because that's what this guy, if I plotted this 0 Reynolds number thing, that's the green line. It doesn't die very fast. It says that you got to keep an hour earlier what happened. But usually that's not the case. This finite Reynolds number is the red curve. So what finite Reynolds number thing says is that maybe a microsecond earlier or milliseconds earlier, this kernel seems to work fine because the red line and the green line agree for a very short time. But then at finite Reynolds number, what happened a second earlier, not that important. Okay, so the Bassett history kernel decays much faster and goes to 0 faster. Okay, so that makes a big difference if you're going to program Bassett history force, because how long should you go back? Because you got to store those values, you got to integrate them, a lot of numerical details. So this faster decay is a very important thing. So this, putting everything together, finite Reynolds number, spatially varying flow, temporally varying flow. You see this finite Reynolds number correction, drag correction, the kernel at finite Reynolds number, you have volume average, surface average, etc. So you may say this is, in a way, is the best available formula you can use for time varying, space varying flow. Okay, it's hard. I'm not saying everybody uses this formula, but I'm saying here you have it, and you can now decide, I will just calculate velocities, undisturbed flow at the center of the particle. Who cares about surface average? And you can do that. There's nothing wrong if that makes sense. If your particle is small, that's fine. You may say, oh, I don't care about Bassett history. Okay, that's fine. Sometimes that works fine. But here is the master equation. Now you can make it smaller. Or on the other hand, people add lift forces. We're going to talk when I come back, okay, which make this even more complicated. It doesn't have any lift force, okay, so that you may have to add. So that's what makes multiphase flow really hard, is that people make approximations or may add new things, okay. But here this is one finite Reynolds number Maxey-Rayleigh-Gachignol equation is an important equation that tells you how you can calculate force on a particle, and it's based on undisturbed flow. Okay.
The Bassett history, the relative acceleration does not contain the convective time.
There's a lot of technical details. Okay. What happens is that this boundary layer growth, which is what the Bassett history, doesn't worry about convective acceleration. Okay. Whereas the added mass force change from little d by dt, which is the partial derivative versus this total derivative makes a difference. So here, this one, basically the difference is d by dt is following the particle, which is time rate of change following the particle. Big d by dt, which is the total derivative, is following the fluid, right? So it's a good observation, and there is no simple explanation. This is how the theory plays out. You have to look at the derivation of this thing. So it matters in the added mass force, but not so much in the Bassett history force. Okay. Yes.
Sir, so when we talk about the Reynolds number, so it is fluid Reynolds number, right?
Yes, thank you. Great question. Here, Reynolds number is diameter of the particle, the length scale. The velocity scale is relative velocity divided by viscosity. Okay. So you have to look at the application and you find what the Reynolds number. If the Reynolds number is very, very small in your application, then you can use BBO equation. You don't need this thing. You may just simply use Bassett history kernel and so on. Now, if the Reynolds number even is around 1 or even larger, then you may have to change both these circle terms. Okay, that takes care of Reynolds number. The rest of them remain the same. Yeah. Any other questions? Yes.
So in the corrected Stokes drag, we get correction for the Stokes drag. So it's like the instantaneous velocity difference, the relative velocity we are using to calculate the instantaneous Reynolds number. Right?
Yeah, absolutely. Yeah. So Reynolds number is a function of time because u is a function of time and t is a function of time. In an evaporating droplet, diameter could be a function of time. So you look at that time, what's the relative velocity, what's the diameter, what's the Reynolds number, and you say, okay, I'm going to calculate drag on that. Now, all the changes that happened do have an effect, and they will show up here. Okay. So a evaporating droplet, this kind of may be complicated, and I don't think people know what it is. That's why people just throw the last term. But at least for us, we will know what approximation we make. So I'm not saying everybody should calculate with all this complication, but at least you will know what you're throwing away or neglecting. Okay.